to show just how useful polar coordinates are in integrals, let's go back and compute an integral that you may have seen before, but may have had difficulty solving. This is the Gaussian, the standard probability density function on the reals given by 1 over root 2 pi e to the minus x squared over 2. This has mean 0, standard deviation 1. It's your classic bell curve. Now, in order for this to be an honest probability density, this function has to satisfy the property that when you integrate it over the entire reals, as x goes from minus infinity to plus infinity, you have to get a value of 1. Now, go ahead and try doing that using single variable calculus techniques. It's really difficult, if not impossible. But now we're going to be able to do it. How do we do this? Let's set up the integral of e to the minus x squared over 2. Let's forget about that 1 over root 2 pi for the moment and just look at the integral of that slightly simpler function. I still don't know how to do it. And my first step is going to be to make the problem more difficult by taking this integral and squaring it. What do we do in that case? Do we just square the integrand? Is that okay? No, that is not okay. Do not do that. Instead, just multiply this integral by itself. Take that and then multiply it by itself. But instead of using x for the integration variable in the second copy of this integral, I'm going to use a different variable. What am I going to use? What, z or smiley face? Well, it doesn't matter what variable name we use. So let's use y. Why? Why? We're going to see. And here comes the part that is a bit subtle, a bit tricky. We're going to use the Fubini Theorem. But in reverse, we're going to convert these two single integrals into a double integral, thinking of them as an iterated integral. What I can do is say, oh, now, as a double integral, this is over the entire xy plane, as x and y both go from minus infinity to plus infinity, and then the integrands multiply together. And by exponent laws, I get e to the minus quantity x squared plus y squared over 2. Integrating this over the entire plane is the same thing as doing that single integral that we want and squaring it. Okay, so what's the advantage in that? Well, this is a little strange. Maybe it would help to visualize what's happening, because this double integral is really a standard 2D Gaussian. And what Fubini is saying is that the integral of this standard two-dimensional Gaussian really breaks down into the product of the one-dimensional Gaussians. And why is this useful? Take a look. There is polar coordinates just sitting there in front of us. When I see that minus x squared plus y squared, that's just shouting out at me, hey, convert that to polar coordinates. And what we're going to see is that the double integral is simpler than the single integral. Okay, so let's work at that double integral, at the integral of e to the minus quantity x squared plus y squared over 2. Now, it's clear that converting this to polar coordinates is the right thing to try. So let's begin by converting the limits of integration. Since I'm integrating over the entire plane in polar coordinates, this converts to r going from 0 to infinity, since r can't be negative, and theta, the angular variable, sweeping from 0 all the way around to 2 pi. The integrand converts to e to the minus r squared over 2. That's nice. And then the area element converts to r dr d theta, and now we see how it's going to work. This is a classic u substitution integral, where u equals r squared, and du is 2r dr. Performing that substitution, doing the double integral, evaluating at the limits, and a little bit of algebraic manipulation gives me minus 2 pi times e to the minus r squared over 2, as r goes from 0 to infinity. That's 2 pi, and that is the square of the integral that we've been looking at. That means that the integral of e to the minus x squared over 2 over the entire reals is square root of 2 pi. That's the reason for that 1 over root 2 pi in a standard Gaussian. And now we have done it. We have finally solved that integral thanks to polar coordinates.